I am Dr. S. Ananda Kumar, Assistant Professor, Department of Mechanical Engineering, Government College of Tirunelveli. I am going to teach MA 8096 Gas Dynamics and Jet Propulsion Unit 2 Flow Through Duct. Unit 2 Flow Through Duct. Introduction. Friction is present in all real flow passages. There are many practical flow situations where the effect of wall friction is small compared to the effect produced due to the other driving potential like area, transfer of heat and addition of mass. In such situation, the result of analysis with the assumption of frictionless flow does not make much deviation from the real situation. Nevertheless, there are many practical cases where the effect of friction cannot be neglected in the analysis. In such cases, the assumption of frictionless flow lead to unrealistic influence of the flow. In high-speed flow, there are through pipeline for long distances of power plant, gas turbine and air compressor, the effect of friction on working fluid is more than the effect of heat transfer. It cannot be neglected. An adiabatic flow with friction through the constant area duct is called a Fano flow when shown in Ketch's diagram. Curves obtained are Fano line. Friction induces irreversibility resulting in entropy increases. The flow is adiabatic since no transfer of heat is assumed. Fano flow. A steady one-dimensional flow in a constant area duct with friction in the absence of work and heat transfer is known as Fano flow. Application. Fano flow occurs in many practical engineering applications of such a flow includes flow problem in aerospace application system, transport of fluids in a chemical process plant, thermal and nuclear power plants, petrochemical and gas industries, various types of flow machineries, air conditioning system, high vacuum technology, transport of natural gas in long pipeline, emptying of pressured container through a relatively short tube, exhaust system of an internal combustion engine's compressed air system. When gases are transported through pipe over a long distances, it is also a practical importance when equipment handling gases are connected to a high pressure reservoir which may be located some distance away. Knowledge of this flow will allow us to determine the mass flow rate that can be handled, pressure drop, etc. In the real flow, friction at the wall arises due to the viscosity of the fluid and this appears in the form of the shear stress at the wall. For in our discussion, we have assumed the fluid to be calorically perfect in viscid as well as. Thus, strictly speaking, viscous effect cannot be accounted for in this formulation. However, in reality, viscous effects are confined to very thin region, boundary layer, near the wall. Effects such as viscous dissipation are also usually negligible. Hence, we can still assume the fluid to be inviscid and take the friction force exerted by the wall as an. As an externally imposed force. In the origin of this force is force of significance to the analysis. The following are the main assumptions employed for analyzing the frictional flow problem in Fano flow. One-dimensional steady flow. Flow takes place in constant sectional area. There is no heat transfer or work exchange with the surrounding. The gas is perfect with the constant specific heat. Body forces are negligible. Wall friction is a sole driving potential in the flow. There is no obstruction in the flow. There is no mass addition or rejection to or from the flow. In thermodynamic coordinates, the Fano flow process can be described by a curve known as Fano line, and it is defined as the locus of state which satisfies the continuity and energy and entropy equation for a frictional flow is known as Fano line. Fano line or Fano curve governing equation. Flow in a constant area duct with the friction and without heat transfer is described by the curve is known as Fano line or Fano curve. We know that from the continuity equation, m equal to rho AC, then m by A is equal to rho C, G equal to MA equal to rho C, where G equal to mass flow density, C equal to velocity of sound, rho equal to density of fluid, then G equal to rho C, C equal to G by rho, then H naught equal to H plus rho equal to f of SH. Substitute the value for rho in the equation H. We get H equal to H naught is equal to 12 G22 f of SH2. The above equation can be used to show a Fano line in H's diagram. In the line, point F is the sonic point lying below or supersonic point lying above or subsonic flow. Since entropy can only increase the process that happen will always coverage to the sonic point F. The curve consists of two branches AM and FP at point F. The flow is sonic, that is m equal to 1. The flow A to F is subsonic, that is m less than 1, and B to F is supersonic, that is m is greater than 1. In subsonic flow region, like A to F, the effect of friction will increase the velocity and Mach number and to decrease the enthalpy and pressure of the gas. In supersonic flow region P to F, the effect of friction will decrease the velocity and Mach number and to increase the enthalpy and pressure of the gas. We know by the second law of thermodynamics that for an adiabatic flow, the entropy may increase but cannot decrease. So the process in the direction F to A and F to B are not possible because they lead to a decrease in entropy. Fano curve are drawn for different values of mass flow density G. When G increases, the velocity increases and the pressure decreases in the subsonic region. When G increases, the pressure increased and velocity decreases in the supersonic region. Importance feature of Fano curve. From the second law of thermodynamics, the entropy of the adiabatic flow increases but cannot decrease. Thus, the path of state along the Fano curve must be towards the right. The subsonic region, the effects of friction will be to increase the velocity and the Mach number and to decrease the enthalpy and the pressure of the stream. In the supersonic region, the effects of friction will be to decrease the velocity and the Mach number and to increase the enthalpy and the pressure of the stream. A subsonic flow can never become supersonic due to the limitation of second law of thermodynamics, but it can approach to sonic, that is m equal to 1. A supersonic flow can never become subsonic unless a discontinuity is present. In case of isentropic stagnation, pressure is reduced whether the flow is subsonic or supersonic. Choking of Fano flow. In a planar flow, the subsonic flow region, the effect of friction will increase the velocity and Mach number and to decrease the enthalpy and pressure of the gas. In supersonic flow region, the effect of friction will decrease the velocity and Mach number and to increase the enthalpy and pressure of the gas. In both cases, entropy increases up to limiting state where the Mach number is 1 and it is constant afterwards. At this point, flow is said to be choke flow. Adiabatic flow of a compressible fluid through a conduit. Flow through pipe in a typical plant where line length are short. The pipe is well insulated can be considered adiabatic. A typical situation is a pipe into which gas enters at a given pressure and temperature and flow at a rate determined by the length and the diameter of the pipe and the downstream pressure. As the line gets longer, friction losses and increase and flow, the following occurs. Pressure decreases, density decreases, velocity increases, enthalpy decreases, entropy increases. The question is, will the velocity continue to increasing until it crosses the sonic barrier? The answer is no. The maximum velocity always occurs at the end of the pipe and continue to increase as the pressure drop until reaching Mach number 1. The velocity cannot cross the sonic barrier in adiabatic flow through a constant conduit of constant cross section. If an effort is made to decrease the downstream pressure further, the velocity, pressure, temperature and density remains constant at the end of the pipe, corresponding to the Mach 1 condition. The excess pressure drop is dissipated by shock wave at the pipe exit due to sudden expansion. If the line length is increased to drop the pressure further, the mass flux decreases so that Mach 1 is maintained at the end of the pipe. The effect of friction of the property of planar flow. So property subsonic, supersonic. Velocity decrease in supersonic, subsonic increase supersonic decrease. Similarly, Mach number, stagnation temperature, density, stagnation pressure and entropy. So this table shows that in subsonic different condition, supersonic also different condition. So the next one, the effect of friction in supersonic flow of the following parameters: velocity, pressure, temperature. Flow properties at m equal to m star equal to 1 are used as a reference value for non-dimensional various properties at any section of the duct. Velocity. So this equation shows the C1 divided by C2. It is a velocity ratio. Velocity ratio equal to M1. M1 1 plus gamma minus 12 M12. So this is the velocity ratio. Similarly, pressure ratio equations. Okay. And applying this equation for section 1 and 2, the temperature ratio is 1 plus gamma minus 12 M12 1 plus gamma minus 12 M22. So variation of flow properties, the next topic. The flow properties, pressure, temperature, density and velocity at m equal to 1 are used as a reference value for non-dimensional various property and at any section of the duct. Temperature. So the temperature ratio is T by T star equal to gamma plus 1 divided by 2 into 1 plus gamma minus 1 divided by m square. Applying this equation at section 1 and 2, then T2 divided by T1, it is a temperature ratio at section 1 and 2, 1 plus gamma minus 1 divided by m1 square whole divided by 1 plus gamma minus 1 divided by 2 m1 square. Then the velocity equation, Mach number m. M equal to C by A, then C equal to m into root of gamma or T. At critical state, m equal to 1, C equal to C star, T equal to T star. Then C by C star equal to M root of gamma T divided by root of gamma T star. Then the velocity ratio. Then velocity ratio, C by C star M into whole gamma plus 1 divided by 2 into 1 plus gamma minus 1 divided by m square whole power 1 by 2. Applying this equation for section 1 and 2, C1 divided by C2 is equal to M2 divided by M1, T divided by T star whole power 1 by 2. Then density equation. Similarly, these are the derivation. Then finally find out the rho 2 divided by rho 1 is equal to 1 by C2 divided by C1. Similarly, pressure equations also P1 P2 divided by P1 equal to M1 divided by M2 whole power 1 plus gamma 1 divided by 2 M2 square divided by 1 plus gamma minus 1 divided by 2 M2 square whole power 1 by 2. Then the stagnation pressure also some equations P naught divided by P equal to T naught divided by T whole power gamma minus divided by gamma minus 1. Then P naught equal to P into T naught divided by T whole power gamma minus divided by gamma minus 1. Considering the section where M equal to 1 and it is its stagnation section, we have P naught star equal to P naught, P equal to P star, T naught star equal to T, T equal to T star. Then these are the derivation for find out the stagnation pressure. P naught equal to P into T naught divided by T whole power gamma divided by gamma minus 1. So these are the equations. Then the next topic, impulse function. Impulse function equal to PA 1 plus gamma m square. Considering the section where m equal to 1 and its stagnation section, we have f equal to f star, p equal to p star, a equal to a star. Then finally find out the f divided by f star. Then next one, entropy. Changing entropy is given by S minus S star divided by R equal to minus ln of P naught divided by P naught star. Then, so this topic is second video. Thank you.